Hi, welcome to this video. The topic is absolute dating. How can geologists measure the ages of rocks and then be able to estimate the age of the Earth as well? So we've been talking about how rocks tell a story, and if we learn how to interpret them by looking at their physical and chemical characteristics, then we can be able to tell the processes that formed them, the environment they were formed, the history of living things and fossils, and how the world has changed over time, and their age, how old they are. So up until the late 1800s, geologists relied on relative dating. This was more of a qualitative approach to dating rocks, and they used principles like the bottom layers are older than the layers above. They also used index fossils in order to be able to compare layers of rock or strata from one area to another. A book I recommend on this is called The Map That Changed the World by Simon Winchester. So in the late 1800s, scientists discovered radioactivity. Marie Curie was one of the scientists that pioneered this research, and along with the help of many other scientists, we now know the activity in rocks that allow rocks to decay, and from there, geologists were given a tool in order to date rocks. This method of dating rocks is called absolute dating. The discovery of radioactivity provided a tool called radioisotopic dating to assign specific years to mineral grains within a rock. So in order to understand radioisotopic dating, we need to understand isotopes. So here's an example with hydrogen. Hydrogen always has one proton. So here in this example, we see the proton. And each of these only has one proton. But you notice that there are different numbers of neutrons. In this example, we have 0 neutrons. In this example, we have 1 neutron. And then in this example, we have 2. So that is different kinds of isotopes of the same element. So now that we know what isotopes are, let's go ahead and talk about how radioactive decay works. The first example is alpha decay. So as you can see from the nucleus here, 2 protons and 2 neutrons were given off from the nucleus, and this is an alpha particle. An alpha particle is basically a helium atom. Helium that we use to blow up our balloons and have parties with. Helium is a byproduct of radioactive decay. It's called an alpha particle. So the result of an alpha particle being released from the nucleus means that we have 2 less protons. And if we have 2 less protons, that means that we have a completely different element, a different kind of atom. So the original atom is a parent isotope, and then the resulting atom is the daughter isotope. The next kind of radioactive decay is called beta decay. So what happens here is that a neutron gives off an electron, which is a beta particle. That's why it's called beta decay. And that neutron then turns into a proton because it has lost that negative charge. So now we have another proton in the nucleus, changing it into a different kind of atom, which is the daughter isotope, and we have added 1 proton. The third kind of radioactive decay is called electron capture. In this type, we have an electron that is being captured by a proton in the nucleus, and therefore the proton reduces its charge and changes into a neutron. So now we have 1 less proton, and because the electron went into the nucleus, it left kind of a hole in its electron shell. And so another electron from a higher energy level can drop down, and the extra energy is given off in the form of an X-ray. Or similar processes can happen, and different kinds of energy can be given off in the form of gamma rays or a neutrino, which is like an electron but with a neutral charge. So those are the 3 kinds of radioactive decay. Alpha decay, emitting a helium particle, beta decay, where an electron is emitted, and then electron capture, which gives off X-rays, gamma rays, or neutrinos. Here we see the periodic table, and as you can see, the radioactive elements are typically the ones that are lower on the periodic table, that are heavier, And these are the ones that have no known stable nuclei. So these are all radioactive elements. There are other ones that are radioactive as well that have radioactive isotopes. So one analogy in order to understand why atoms are radioactive and why they decay is imagine being pushed into a room with lots of other people and it's super crowded and very uncomfortable. What's going to happen naturally? Well, people are going to start leaving the room. And eventually, people will, like half of them will leave. And so that is represented here. Like this is a very crowded room. And here is where half of the people have left. And that is kind of an analogy of a half-life of a radioactive element. So that's when the time it takes for half of a mineral to decay. And then after a while, people are going to keep leaving and then another half-life goes by. So this one is half of this one. So eventually people are going to keep leaving and it's going to become a little more comfortable. So people won't leave quite as quickly, but eventually the room is going to clear out after a while and then we won't have any more people in the room. So that is kind of like a good analogy of radioactive decay. Not exactly, but it helps us to understand why this is happening. So one of the tricky things about radioactive decay is that we don't know exactly when a nucleus is going to decay. We can't predict that, just like we can't predict when one person is going to leave the room. But if we observe radioactive decay over a period of time, then we can collect enough data in order to calculate probability. So it's very similar to rolling dice. We don't know exactly when we're going to roll a pair of sixes, but with probability calculations and formulas, we can pretty accurately predict how many sixes will roll within a certain number of turns, or if we're rolling at a certain rate, how long it's going to take to roll sixes, and so on and so forth. So this is very similar to how scientists calculate the half-life of radioactive elements. So all radioactive elements follow a certain decay pattern. Here we have 100% of the parent material, and over time it's going to decay to 50%. So that's right here at 50%. And what happens is that as the parent material is decaying, the daughter isotope is increasing because it is decaying into the daughter isotope. So the daughter isotope is represented by this line, and here we would have 50% of the daughter isotope and 50% of the parent isotope. So as you can see, initially, there is a relatively shorter amount of time for the parent isotope to decay by 50%. But then it starts to slow down. So as it decays into 25%, now we have 75% of the daughter isotope. Then the decay tends to slow down. So eventually it's going to flatten out and until it becomes 0 and there is no more parent isotope left. But the daughter isotope is increasing as it decays into the daughter isotope, and then we have 100% of the daughter isotope. In this formula, we see the quantity of the substance remaining, so that's the percent of the parent material that is left in a substance. We see the initial quantity of the substance, and then we also see the time elapsed, so that's represented by T, and the half-life of the substance. So as long as we know 3 of these things, then we can calculate for the other one. Here are some examples of known half-lives. As you can see, uranium-238 is huge and it has a very, very long half-life. Carbon-14 has a half-life of just over 5,000 years, all the way down to one of the isotopes we saw earlier, hydrogen-3, tritium, which is 4,500 days, so it has a very relatively short half-life. And then sodium decays, half of it decays only within 15 hours. So within a day or two, sodium-24 will completely decay. So this is a microscopic picture of a zircon, which is very useful for dating rocks because at the time of formation, there is no lead that's present in the zircon. So any lead that's found in the daughter isotope is the result of radioactive decay from the radioactive uranium isotope. So in this slide, we see the decay chain of uranium-238 to a stable lead-206 isotope. As you can see, we start out with the radioactive uranium isotope, and then it goes through a series of alpha and beta decay, and then eventually it ends up as a stable lead isotope in the end. So in conclusion, you can determine the age of a rock if you know the half-life of the parent isotope, or the rate of decay, the current percent of the parent isotope, and the current percent of the daughter isotope. So one thing that we do have to keep in mind is that we have to use the right kind of material in order to date the right kind of thing. So as you can see, carbon-14 decays to nitrogen-14. And carbon-14 is found in organic material. It's not found in inorganic rocks. So it's good for dating organic remains like trees or archaeological artifacts that were made from organic materials. And it only has a date range of up to 60,000 years. So potassium to argon is a good way to date rocks because it is found in volcanic rocks. And then we've already talked about the uranium to lead dating, which is also found in volcanic rocks. And they have a very much longer half-life as well. So those are very common ways to date rocks. I think one thing that is difficult to think about is deep time, because we typically measure our time in seconds, days, years, or even recent history up to millennia. But thinking of time in millions and billions of years is not very common. It's a little hard to wrap our heads around. So when I think about how old the earth is, I think about the great care and love that God put into creating the earth and maintaining its processes over so many years in order to create a very habitable and comfortable home for us. And it helps me to think about how we collectively can take care of this home that He has so lovingly given to us and provide a more hopeful future. This quote by Marcia Bjornerud in her book Timefulness says this, and I'll just end with this. The earth itself, with its immensely deep history, is a communal heritage and universal mentor that may help us find a set of shared values. Studying its past may cause us to reconceive ourselves as fellow citizens of a profoundly mysterious planet that we urgently need to know better.